Welcome to lecture number 15 of the course Nonlinear Structural Analysis, Theory and Applications. Let us recall what we have done so far in the course. So, first we started with reviewing the concept of linear structural analysis, then we studied the direct stiffness method, and then we have introduced you to the concepts of nonlinear structural analysis. We looked at three sources of nonlinearities: the material nonlinearity, which basically stems from the nonlinear stress strain response, and the geometric nonlinearity, which comes from the nonlinear RS relationship, that means the equilibrium in the deformed configuration, and the nonlinear VR relationship, or that is the nonlinear compatibility. Okay. So, what we will do now, we will talk about the material nonlinearity, which comes from the nonlinear stress strain relationship. Okay. So, let us get started. So, what we will discuss in this lecture, we will talk about the tensile test of metals, okay, and then we will look at brittle versus ductile, loading, unloading, reverse loading, and so on. So, this is basically the beginning of our journey on the material nonlinearity. Okay. So, let us start at a very basic level of tensile test. I am sure many of you or maybe all of you have done the tensile test of mild steel coupon in your undergraduate laboratory course. Okay. So, this is one of the accepted standards to obtain the constitutive relationship or the stress strain relationship for a wide class of materials. Okay. So, for steel, structural steel, what we do, we take a specimen like this. Okay. So, if the cross section of the specimen is rectangular, then it is basically a flat. Here at the ends you have a larger cross sectional area, because this will go into the machine, the UTM, universal test machine, and will get gripped here at the ends. Okay. So, here the area is increased, okay. And if you have a circular cross section, then the specimen looks like this. Okay. So, this distance is called the gauge length, okay. And we mount the specimen and we put extensometer between the two ends of the gauge and measure the deformation as we apply or as we pull the specimen. Okay. So, if we look at, let us say this is my specimen, right. If I am looking at the state of stress anywhere within the specimen, then what kind of stresses we will get? We will get uniaxial state of stress. This will be subjected to only the normal stress. Okay. So, here again I am showing the extensometer. So, between these 2 points you have connected the extensometer, and AB is called the gauge length, the length of which is denoted by L0. And here I am writing the diameter at the gauge is D0. Now, for your information, if I go back one slide, so the dimensions, this A, W, L, B, C, all those dimensions are given in this ASTM standard ASTM E8, which you will see at the end of this lecture in the reference slide. Okay. So, basically within the gauge length the state of stress is uniaxial, right. So, if I pull the specimen, okay, which is let us say mild steel, right, then you can measure the force. There will be a load cell which will measure the force in the specimen, and using the extensometer we will measure the deformation over the gauge length, right. So, if I plot the force versus deformation, so I can get a curve like that. Okay. Let us say this is for mild or low carbon steel, where the carbon content is typically 0.05 to 0.3%, right. Now, as you can understand that this force versus deformation relationship depends on the length, okay, and the cross sectional area of the specimen. If you change it, this will change. So, what we do, we convert this force deformation relationship to stress and strain. Okay. So, we define the normal stress or the engineering, or also called the nominal stress, which is the load divided by A0. A0 is the initial cross sectional area of the gauge section. Okay. And we define the normal strain or the engineering strain, which is epsilon x, because my x axis was vertical, that means along the length of the specimen. Okay. So, which is epsilon x is L minus L0. L is the deformed length and L0 is the original length divided by L0, that is my strain. Okay. So, we can plot the stress versus strain instead of the force versus deformation. Okay. Now, in some engineering problems or in some engineering applications, for example, metal forming, the strains can be large. Okay. So, if the strains are large, then what we do? We define what is called true or natural strain, which I am writing as epsilon true. If we consider an incremental strain d epsilon true, which is instantaneous change in length dl divided by the current length L. Okay. So, now if I integrate it on both sides, so if I integrate between 0 to epsilon true, initially there was no strain, okay, and then at some point the strain is epsilon true strain. So, then I am integrating that. So, on the right hand side, what was my initial length was L 0, the final length is at some point it is L, right. So, if I integrate this, I get this natural log L by L 0. Okay. So, then I can write this L is equal to L 0 plus the incremental, the change in length delta L. So, L 0 by L 0 is 1 and delta L by L 0 is my engineering strain epsilon. So, the natural strain or the true strain is equal to natural log of 1 plus the engineering strain. Okay. I will show you how does the true stress strain response looks like, but before that let me also define the true stress. Now, if you can understand that when I am pulling the specimen, okay, the cross sectional area of the specimen will reduce. Okay. So, there is a change in the cross sectional area as the load increases. So, what we can do? We can define what is called a true stress, that is load divided by the current cross sectional area. When the load is F, what is the value of the cross sectional area? That is A. Okay. So, if we consider the gauge section is incompressible, that means the volume is constant, okay, then what we can do? We can say, well, A 0 was my initial cross sectional area and L 0 is my initial gauge length. So, the volume is A 0 into L 0. After some deformation, the cross sectional area is A and the gauge length is L. So, the volume remains constant. Okay. So, if I do that, then the true stress can be written as F by A is written as F by A 0 into A 0 by A. Okay. Now, using this equation, I can write, so F by A 0 is my sigma and A 0 by A, using this equation I can write is L by L 0. Okay. So, what is my L by L 0? Well, L by L 0 is nothing but I can say L is equal to L 0 plus delta L. Now, L 0 by L 0 is unity and delta L by L 0 is my engineering strain epsilon. Okay. So, this is the expression for true stress. Let me tell you that sigma true is always going to be greater than the engineering stress sigma, because A is going to reduce. So, therefore, sigma true will be greater than sigma. Okay. Now, note that these two equations, equation 2 and 3, are based on the assumption that over the gauge length, the reduction in the cross sectional area is the same along the gauge length. Okay. So, it is everywhere you are getting delta A decrease. Okay. But this is not always the case, as I will show you later. When you take a mild steel specimen, after it reaches the tensile strength, what will happen at some point, at somewhere within the gauge length, there will be necking. That means significant reduction in the cross sectional area. Okay. So, in that case, this equation and this equation, these two are not valid. If you want to get the true stress, you have to measure the actual cross sectional area and divide it by that, then only you will get the true stress. Okay. So, here I am showing you typical stress strain diagram for different materials. So, on the left hand side, these are for different steel. This is taken from the engineering mechanics by Professor Popov. So, vertical axis I am plotting the sigma or the stress, and the horizontal axis is the strain. So, if you take tool steel, the steel that is used to manufacture tool, so it is something like this, okay, very high strength but brittle. And then this is for low alloy high strength steel, and these are for low carbon or mild steel. Okay. Here on the right hand side, we have stress strain response for different materials. For example, this is the low carbon steel, which is not shown completely because the range here is, the strain range is smaller. Here we are going up to 0.4, here it is much smaller. Okay. So, therefore, for low carbon mild steel it is shown only up to this, right, and this is for aluminum alloy, this is for cast iron. So, cast iron, let us say this top is under for tension, this is for tension, okay, and this is for compression, right. Okay. So, as you can see, cast iron shows very different behavior. This is tension and this is compression. Okay. Whereas, for concrete, well, concrete is very weak in tension. So, we are showing the behavior of concrete in compression. We will study more about the concrete stress strain response later on. So, this is just a schematic showing you qualitatively the difference in stress strain response of various materials. So, let us say this is for wood and this is for rubber. Okay. Now, let us talk more about the stress strain response for mild or low carbon steel. Okay. So, if I take a mild steel specimen and do the tensile test and plot the sigma versus epsilon, there are certain important things that we notice. First, the stress versus strain or stress strain remain proportional up to point A. Okay. So, point A is called the proportionality limit, and what is the ratio? The ratio is, the slope is called the Young's modulus, okay, that is sigma over epsilon, right. So, that is called the modulus of elasticity or Young's modulus. Okay. Now, if you keep loading, beyond point A, so which I am showing here, some little bit exaggerated. So, point A to point B, the curve is nonlinear. That means, sigma is no longer proportional to epsilon, but it is elastic. That means, this point is called the elastic limit. So, if you unload the specimen from here, it will come back following the same path. So, although A to B is nonlinear, but it is elastic. Okay. If you continue loading, then what happens? Material will starts to yield, and mild steel shows a behavior that, okay, after point C, this stress suddenly drops, okay, and then material continue to deform, which I am showing again here plastically. Okay. So, this part from here to here, this is basically our linear, okay, linear region, and then from here to here is what is called perfect plasticity, right, that the material continues to deform without any change in the stress level. Okay. There will be a little bit of zigzag. I am not getting into the reason why this happens. If you are interested in material science, you can go ahead and read, okay, but we are not getting into the reason. Okay. So, now let us say if we unload the specimen from here, what will happen? The material will unload elastically, okay, and this slope is going to be same as the original or the initial elastic slope, right. So, this will unload with E, and if you from this point, if you again reload, it will follow the same straight line. Okay. So, D is called the lower yield point, which is what I have written here. Okay. Now, let us note that the upper yield point, which is this point, is very sensitive to rate of loading and accidental bending stresses and any irregularities that might be present in the specimen. Okay. So, D is called the lower yield point, and E, here at point E, what happens, the material starts to take more and more load, the load increases. Okay. There are changes in the internal atomic characteristics of the material. Okay. So, the material continue to take more and more load, and eventually it comes to the ultimate stress, which we call the ultimate tensile strength and denote by sigma u at point F. Okay. And after that, so this region is called strain hardening. The material continues to take more and more load, okay, of the specimen. And then eventually, if you continue stretching the specimen, okay, then eventually the material will fracture, and in this region what will happen, as I am trying to show you here. So, somewhere within the gauge length, there will be significant reduction in the cross sectional area, which we call necking, right. So, necking will form and eventually the material will fracture. Okay. So, that is point G. This curve is called your engineering stress strain response. That means, the stress is calculated as the load divided by the original cross sectional area, and strain is simply the change in length over the gauge length divided by the original length. Okay. Now, if I plot this true stress versus true strain, then how does it look like? Well, up to point E, that means the onset of strain hardening, there is no significant difference between the engineering stress strain and the true stress strain response. So, up to this you get the same thing, and after this what happens, the cross sectional area of the specimen starts to reduce. Okay. So, that means the true stress increases and it goes like this. Now, after this, if you have to get the true strain, true stress strain response, what you have to do? You have to measure the actual cross sectional area. Okay. So, this is the behavior. So, like I said, AB, this part is elastic but nonlinear, but like I said, this point C is very sensitive to rate of loading, any imperfection and so on. So, there, and it is very difficult to capture also. So, for all practical purposes, what we do? We take A, B and D are to be only one point. So, these are taken to be the yield point. Okay? And this upper yield point C is basically ignored, right. So, that is what we do. So, just to give you a sense of numbers, typical values for mild steel, the yield strain is like 0.1 to 0.2%. The strain at onset of strain hardening, that means this number is somewhere between 15 to 20 epsilon y, where epsilon y is the yield strain, and the strain at the ultimate stress, that means this number is somewhere between 100 to 150 epsilon y, and at fracture this is between 0.3 to 0.4. Okay. Other metals, unlike mild steel, do not show a sharp yield point and nor a plastic flow. What is plastic flow? Well, this region is also called plastic flow, where the material continues to deform without any change in stress. Okay. So, most metals neither show a sharp yield point nor a plastic flow, and the stress strain response looks something like this. So, in that case, how do we define the yield strength of the material? So, it is defined rather arbitrarily, okay, and how it is typically done? We defined yield strength as offset yield stress corresponding to 0.2% strain. So, what we are doing, if we draw the initial tangent here, which is like this, and you offset it by 0.2%, that means 0.002 strain. So, then you draw this line which is parallel to the initial tangent, and it intersects the curve at this point, which we call sigma y, the offset yield stress, okay, or the yield strength of the material. And this is also called initial yield stress. Why initial yield stress? That you will see, in the subsequent slides, right. So, if we continue loading beyond this point, what happens? The material continues to take more and more stress, or the specimen takes more and more load. Okay. So, it increases monotonically, but the slope of the curve reduces, as you can see, the slope here versus the slope here. The slope reduces continuously, and it reaches the ultimate at, let us say, here in this figure at point E. Okay. So, now let us talk about ductile versus brittle materials. So, if we plot the sigma versus epsilon response for ductile and brittle material and compare them. So, what is a ductile material? A material that is capable of withstanding large strain without any significant change in the stress is called ductile material. Okay. For example, mild steel is a ductile material. On the other hand, brittle materials are not capable of withstanding large strains. Okay. They fail suddenly. So, here I am showing schematically the stress strain response of a brittle material, which let us say after proportional limit it only takes a little bit of strain and then it fails all of a sudden. On the other hand, a ductile material after the proportionality limit can take large or can withstand large amount of strain, okay, without much change in the stress level. And so, the example of brittle materials are cast iron, concrete and glass. Example of ductile material, as I said, mild steel. Okay. So, note that sigma epsilon behavior of ductile material is very similar in tension and compression, whereas brittle materials show very different behavior in tension and compression. If you recall, a few slides back I showed you the cast iron tension compression behavior or the stress strain behavior in tension and compression. Let me go back to that figure. So, here if you see that this is the stress strain response of cast iron in tension and this is the stress strain response in compression. Consider concrete. Concrete is very brittle material, it is very weak in tension, and in compression, well, it can take load, right. So, the concrete behavior, if it is confined versus unconfined, we will talk about those as we go along, okay. But this is the behavior in compression. In tension, well, it can just go a little bit and then fail all of a sudden. So, brittle materials show different behavior in tension and compression as compared to ductile material, which typically show very similar response in tension and compression. Okay. So, if we look at the failure surface, so here this is a ductile material A572 steel, this nomenclature is based on ASTM, and this is aluminum 6061 T6 aluminum alloy. What you can see, a cup cone kind of a failure surface, and you can see necking, right, you can see necking. Okay. So, that is the characteristic of ductile failure in a tension test, and it happens due to slip in shear along planes which are 45 degree with the axis of the rod. So, if you look at, this is the axis of the rod. So, along the 45 degree angle you are basically getting slip, right. On the other hand, for the brittle material, what you get? You get a sudden failure, which is basically a kind of square separation, okay, which is also called a cleavage or separation fracture, for which is typical of brittle materials. Okay. And there is no necking in the case of brittle materials. Now, let me talk about loading, unloading and reloading, what we mean by these three terms. So, let us begin the discussion with three different behavior: linear elastic, non-linear elastic and inelastic. So, linear elastic means your sigma epsilon relationship is linear. You go like that, increase and unload like that, okay, and the slope is modulus of elasticity E, right. So, any material that is within the proportional limit behaves linear elastically, we all know that. On the other hand, nonlinear elastic means that the stress is no longer proportional to strain, but you go along this path, and when you unload it comes back following the same path, then we call it elastic, but it is nonlinear. So, it is nonlinear elastic. Where do you see this kind of behavior? Well, rubber, elastomers or soft biological tissues up to a large strain can show this kind of nonlinear elastic behavior. On the other hand, if we look at inelastic material, for example, structural steel, okay, the stress strain response is something like this. Let us say it is not mild steel, for mild steel you will have a well defined yield point. So, it is like this, right. Now, if you unload from here, it comes back following the initial slope, okay, and if you reload, it goes like that. Okay. So, that means when you come back from here, you have some permanent deformation in the specimen. So, which is the plastic strain, permanent set or plastic deformation, and then this much strain you have been able to recover, which we call the epsilon EL, the elastic recovered strain, and the total strain is equal to the sum of the elastic plus the plastic, and this area is the measure of the energy dissipated due to this plastic deformation. So, we will talk more about this, okay, over the next few slides. So, examples include metals, concrete and so on. Okay. So, mostly we will focus our discussion on inelastic materials, right. So, I am showing you a better schematic of inelastic material. This is sigma versus epsilon. Let us say this is my initial yield stress. Okay. Initial yield stress means the one, let us say we have calculated using the 0.2% offset method, right. Now, I have taken the specimen and I am loading it monotonically. I have taken it beyond sigma y0. Okay. So, if I have taken it beyond and I have come to this point A, okay, and now if I unload, as I was saying, I will unload elastically with the slope that is the initial elastic modulus, okay, and if I reload, I will go like that. So, this is my plastic strain and this is my elastic strain which I have been able to recover. So, the total is equal to epsilon P plus epsilon elastic. Okay. Okay. So, whatever I stated is written here, OB is plastic strain and this is the elastic strain, right. Now, if you decide that okay, after full unloading, that means you have come to this point and you decide to reload the specimen again in tension, that means you follow this path. So, what is happening now? Now, the stress strain response of the material is elastic up to this point. So, that means up to a stress sigma A, as if the material is yielding at sigma A, but actually the initial yield stress of the material was sigma y0, right. So, what is this point called? This is called subsequent yield stress. Okay. So, for most metals, what happens if you go past this sigma y0, the stress strain curve keeps rising, okay, with of course the reducing slope, and sigma A is greater than sigma y0. That means, the subsequent yield stress is actually greater than the initial yield stress. In other words, I can say that the material basically has a memory. Material remembers what you have done to it. Okay. You have the initial yield stress is, let us say, here, okay, and you have taken it to this point. So, the material knows that it has already gone past the yield stress. Okay. In the next time when you load it from here, it behaves elastically. Okay. So, this ability of the material to withstand greater stress after plastic deformation is called strain hardening or work hardening. Okay. For some materials, the slope of the curve becomes negative after failure. For example, this can go like that. Okay. Then we call that is strain softening, and for example, concrete or rock under simple compression shows this kind of strain softening response. Okay. But for metals, we see the strain hardening, right. So, now let us talk about reversed loading. Reverse loading means, let us say if I take a ductile material and I do a tension test, I get a behavior like that. If I do a compression test on the same ductile material, I get a very similar response. Often we assume that the tension compression responses are the same. Okay. Now, if I take it to, let us say, this point and decide to unload, so here my unloading is completed. Now, if I take it in the opposite direction, okay, so let us say this is tension and this is compression. Okay. So, at this point I have unloaded, now I am taking it to the compression, right. What happens? The material remembers that it was taken to a stress level that is well above the initial yield stress sigma y0, okay, and then when it goes in the compression, it yields at a much smaller stress sigma y double prime. Okay. So, the plastic pre-straining in tension, plastic means you have taken it beyond sigma y0, affects your sigma epsilon curve in compression and vice versa. Vice versa I will explain. So, that means the sigma y double prime is smaller than the initial yield stress. So, it is yielding at a much smaller yield stress, okay, and sigma y0 is of course smaller than sigma y prime, which is this number here. Okay, and this is called the Bossinger effect. Okay. So, now if you, let us say here you are in compression, if you go in the, let us say you unload and then you decide to load in tension. So, then what happens? Let me draw it. You go like that, okay, and then it starts to yield. It starts to yield like that. Okay. It yields early. So, does not matter whether it has gone to tension first or compression later, it can happen if you take it beyond the yield stress in tension and then when you go into compression, it shows the Bossinger effect and the vice versa. Okay. So, it is usually present whenever there is a stress reversal, that means tension to compression or compression to tension. Okay. Now, here I want to note that there is no one-to-one correspondence between sigma and epsilon in a plastically deformed solid. What I mean by that, let us see if I take a strain here, okay, what is the stress? Is it this number? Is it this number? Which one it is? Well, I do not know, because the material behaves in a path dependent manner, or in other words, the material has a memory. It remembers in which path you have taken it to, okay, and it will follow. For example, if the material was going like this, then at this strain the stress is here, or if the material was taken like so, you are going in this direction, then at this strain the stress value is that. Okay. So, therefore, sigma is not a function of epsilon alone, sigma depends on the loading history. Therefore, the material is called load path dependent or hysteretic. So, inelastic materials show load path dependent behavior or hysteretic behavior. So, therefore, now if you recall, when we are talking about path dependent versus path independent state determination in the previous lecture, you will see that the iteration, the Newton-Raphson iteration that we are doing, okay, is just for our convenience. We are trying to determine the equilibrium position. It is a numerical method. It is not the actual behavior of the material. Therefore, we have to always do path independent state determination, because the material shows path dependent or hysteretic response. Okay. So, what we have discussed in this lecture? We have discussed time independent behavior, sigma epsilon curve for tension or compression, which is independent of rate of loading. We have not considered any rate of loading, which is reasonably accurate for structural metals at room temperature under static load. But the rate effect can become important if you have dynamic load, especially let us say earthquake or blast. But structural steel do not show a lot of rate dependency. It depends on the composition of the material, but there are other materials like viscoelastic material, there are shape memory alloy materials which can show rate dependent behavior. Okay. Also in this lecture, we have not talked about any temperature effect. The stress and response that I showed you here schematically, okay, are at room temperature. At high temperature, the stress and response can become significantly different. Okay. So, with that, these are the references that we have used in this lecture. So, what we will do in the next lecture, we will talk about some idealization of the stress strain response, so that we can perform nonlinear structural analysis considering the material nonlinearity, which basically comes from your nonlinear sigma epsilon relationship. Okay. So, thank you and see you in the next lecture.